You ever get that feeling that there's a hidden layer of rules governing the world? You know, like a secret language that describes everything from a snowflake to the laws of physics? Well, there is. It's called group theory, and today we're going to decode it.
And it all kicks off with a really weird question. What on earth does a simple shape, like a triangle, have to do with a math equation that stumped the greatest minds for centuries? The answer? Well, it's the key to one of the most powerful ideas in all of science. To get to the bottom of this, we've got to start with something we all kind of get intuitively. We're talking about symmetry, those hidden rules that govern the objects all around us.
Okay, so take a look at this equilateral triangle. Now, if you were to close your eyes and I rotated it by 120 degrees, when you open them, it would look exactly the same. That's one of its symmetries. Or I could flip it over an axis, and again, you wouldn't know I did anything. It turns out there are exactly 6 of these moves, 3 rotations and 3 flips, that leave this triangle looking untouched.
But here's where it gets cool. The rules change when the shape changes. For a square, you've got more options. You can rotate it 90 degrees, 180, 270. You can also flip it horizontally, vertically, or even across its diagonals. You add it all up, and the square has a total of 8 of these special moves. Each shape has its own unique family of symmetries.
So you're probably starting to see a pattern here, right? As we add more sides, the number of symmetries just keeps growing. This pentagon, it has 5 ways to rotate and 5 ways to flip, giving it a grand total of 10. It's like every shape comes with its own little instruction manual of allowed transformations.
All right, so let's lock in a clear definition. A symmetry is just any transformation, a move like a rotation or a flip, that leaves an object looking completely unchanged. The important thing isn't whether it moved, it's whether it looks the same after the move.
So just to make it super clear, rotating a square by 90 degrees, yes, that's a symmetry. But rotating it by, say, 45 degrees? Nope, not a symmetry because it ends up looking tilted. And stretching the square? Definitely not a symmetry. You've changed the actual shape. These rules are very, very specific.
Thinking about these rules leads us to a really fascinating place. What if we treat these symmetries not just as properties, but as moves in a kind of game? A game with a very special structure.
Let's go back to our square. Here are all 8 of its symmetries laid out. You've got the do-nothing move, the 3 different rotations, and the 4 different flips. Each one of these is a distinct, legal move we can make in our game.
Now here is the absolute key idea, the thing that makes this whole system work. What happens if you combine 2 moves? Let's say you rotate the square 90 degrees and then you flip it horizontally. The result is exactly the same as if you had just done a single flip along one of the diagonals. Any 2 moves you combine always land you on another valid move in the set. The system is totally self-contained. It's a closed loop. And this self-contained set of moves, that is what mathematicians call a group.
Okay, I want you to hold that thought about closed loops and self-contained rules, because we are about to make what feels like a completely random jump, from geometry all the way over to algebra, and a puzzle that drove mathematicians crazy for generations.
We all remember this from school, right? The quadratic formula. It's like a magic recipe. You just plug in your numbers, your a, b, and c from any equation with an x squared in it, and boom, it spits out the answer. It's a general formula that just works every time.
So after they cracked the quadratic, mathematicians found similar, though way more complicated formulas for equations with x cubed and x to the 4th. The next steps seemed obvious, right? But for hundreds of years, nothing. No one could find a general formula for the quintic, an equation with x to the 5th power? Why? What was so special about the number 5?
Now, to be really precise, what they were looking for was a solution by radicals. That's just a fancy way of saying a formula, like the quadratic one, that only uses the basic stuff: adding, subtracting, multiplying, dividing, and taking roots, like square roots, cube roots. You get the idea. They were looking for a specific kind of elegant answer, and for the quintic, it seemed impossible.
The answer didn't come from finding a more clever formula. It came from a young genius who invented a whole new way of seeing the problem, a secret language that would connect these 2 worlds we've been talking about. This is Évariste Galois. I mean, what a story. He was this brilliant, fiery French mathematician who did his most important work as a teenager, before he was tragically killed in a duel at just 20 years old. In the notes he frantically wrote down the night before he died, he basically solved the quintic problem. And this was his profound insight. He discovered that every single equation has a group attached to it, a group that describes its deep fundamental structure. And he proved that an equation can only be solved with a nice simple formula if its group is solvable, which basically means its structure can be broken down piece by piece into simpler steps.
And here it is! This is the mind-blowing connection. Galois realized that every equation has a family of symmetries, just like our triangle and square. But instead of the symmetries of a shape, it was the symmetries between the equation's answers, its roots. He saw that if you shuffled the answers around, they followed very specific rules, just like the corners of a triangle when you rotate it. He stopped looking for the answers themselves and started studying the structure of how they all related to each other.
This one revolutionary idea didn't just solve an old problem. No, it changed the entire direction of mathematics forever.
So why can't you solve the quintic? Remember how a solvable group can be broken down into simple steps? Well, it turns out the group for the quintic, you can't do that. Its structure is too rich, too tangled. It's like a perfectly woven knot that can't be untied into a simple straight line. And because that underlying symmetry is so complex, no formula using just basic arithmetic and roots could possibly exist to describe it.
The legacy of this discovery is just immense. Galois single-handedly shifted mathematics from being about finding answers to specific problems to understanding the abstract structures that govern everything. Group theory became this universal language for describing symmetry anywhere you find it, from the interactions of subatomic particles in physics to molecular structures in chemistry, all the way to the modern cryptography that keeps our information safe online.
And this brings us right back to where we started. That strange connection between a shape and an unsolvable equation. It's symmetry. It's a hidden structure dictating the rules of what's possible and what's not. Which leaves us with one last big thought. If a deep, invisible structure like this is running the show in the world of mathematics, what other hidden structures are quietly shaping everything else we see around us?